Hello everyone, my name is Timothy Murewa Joseph. In this video, I'm going to teach you the energy of simple harmonic motion. But to start with, I would like to discuss a few things about this energy of simple harmonic motion, especially the theory. I'm also going to show you the equations that you can use for all the calculations. So let's begin. According to Hooke's law, the extension E produced in an elastic body is proportional to the applied force F, provided the elastic limit is not exceeded. Yes, and then we have the mathematical representation of this law, giving us F is directly proportional to the extension E, as you can see it here, and then our F is equal to Ke, where the K stands for the spring constant or the stiffness of the spring, or you can also say it stands for the quality or the type of spring that it is. So when we rearrange it, we have our K, that is when we rearrange this equation, we have our K as F divided by E, the force divided by the extension E of the spring, and the unit for it is Newton per meter. Okay. When a spring is stretched or compressed, work is done on the spring. And then we have this simple equation, which means work done is equal to the force applied multiplied by the distance. Force applied multiplied by the distance, or you can say that W equal to F times X, which is also force times the displacement of the spring. So when a spring is stretched, the effort F varies from 0 to a maximum value. Therefore, we use the average force to calculate the work done in stretching a spring. If work is done on a spring, then the spring must possess stored energy, which is known as elastic potential energy. And then the equation for that is this. This is our potential energy given as 1/2 multiplied by K times the displacement, our X, that is the square of the displacement. So our X stands for the displacement, and K have said that it stands for the spring constants. As the spring vibrates back and forth, the potential energy is converting into kinetic energy and then back to potential energy again when it returns to equilibrium, and then back to kinetic energy again, and so on and so forth. So it continues like that. And then we have our kinetic energy given as half mv square. And then we have the total energy, which is the sum of the potential energy and that of our kinetic energy. Let's consider some examples. Here we have the first example. An object vibrates at the end of a vertical spring with a spring constant given as 121 Newton per meter. If the potential energy of the object is 2.20 joules, what is its displacement? Okay, so let's solve this question. So write a solution. And then we look at the parameters that we have in this question. So we have our spring constant, which is given as 121 Newton per meter. And then we have the potential energy given as our potential energy is 2.0 joules. And then we are asked to calculate the displacement. So that is X, or the extension E, if you want to call it. So X Okay, so we're going to apply this formula. So let's apply this formula. So we know that potential energy is given as half. So we have K, that is the spring constant, and then x squared. So we are going to make use of this formula, this equation. So all we need to just do here is to substitute the value that we have, and then we are going to get the result. So we have our potential energy as 2.20. So we write it as 2.20 equal to 1 over 2 times the spring constant, which is given as 121, then times the our x squared, which is the displacement. Okay, so here we just cross multiply, and when you cross multiply, you are going to have 4.40 equal to 1 times 121 is 121 times x squared. So we should have 121 x squared. So this is the displacement. So we're looking for it. Therefore, we say that our x is equal to 4.40 divided by 121 in square root. If you want the short way, okay, without wasting much time. Okay, so we have so when you find the value of this, so this is going to be 2 points. Everything here will be 0.04. So divide this by this and take the square root. So we should have root 0.04. Yes. Okay. And then therefore we can say that when you take the square root, we say that the square root of this is 0.2, approximately 0.2, and our unit should be in meters, so 0.2 meters. So this is the displacement. So its displacement is 0.2 meters. So you can see here, 0.2 meters. So this is how to apply this formula, this equation. Okay, let's consider another example. So I will take this away. Another problem. Okay, so let's see another problem. So here is another problem. A force of 10 Newton extend a spring of natural length of 1 meter by 0.02 meter. Calculate the length of the spring when the applied force is 40 Newton. Okay, so let's get rid of this working. Again, first thing first, so we try to bring out all the parameters that we have in the question to make our work easier. So we write solution. So what do we have? So we have the force here, which is giving us 10 newtons. The force of 10 newtons. Okay, yeah, it's correct. 10. What do we have again? The original length of the spring is 1 meter, and then we have the extension G, which is 0.02. That is the displacement. So we write the extension E given as 0.02 meter. Calculate the length of the spring when the applied force is 40 Newton. So we have to calculate the length of the spring when the applied force is 40 Newton, and this can be. So in this question, we are going to find the spring constant first because it is not given and we will need it for our calculation. So spring constant is not given, so we need it, and then when we find our spring constant, then we can now calculate the length of the spring when the applied force becomes 40 newtons. So firstly, spring constant is given as force over the extension E, so which means we are going to have 10 Newton divided by 0.02, 0.02, and then when we divide this 10 divided by 0.02, so what do we have? Can someone press calculator? Yes, we should have 500 if I'm correct. Should have 500. 10 divided by 0.02. So we have 500, so which means 500 Newton per meter. So this is the constant of the spring. So we have gotten it. Then we put the units. Please don't forget to write the units. Units are very important in physics or generally in science, so to differentiate a given quantity from another. So we have spring constant as 500 Newton per meter. Then we can now calculate the length of the spring when the applied force becomes 40 Newton. So when force uh, force F is now 40 Newton, so we can calculate that also applying Hooke's law, where our force is given as KE. So the first line is we're looking for the length. The force is 40, so we just substitute again. 40 equal to spring constant multiplied by the extension E that we're looking for. So we say E. So we are going to have, therefore, our E is going to be 40 divided by 500. 40 divided by 500. So what are we going to have? So 40 divided by 500 is 0.0, no, 0.08 meter. Therefore, we can say that the length of the spring will become length of spring now, which is length, the total length of spring is 1 plus, that is the original length plus the extension E, which is 0.08 meters, and then we should have 1.08 meter. Yes, so 1.08 meter. So this is the total length. So the original length is 1 meter, for instance, and then when the force of 40 Newton was applied to it, it extended by 0.08 meter. So we add the two together to get the total length, which is this. Okay, so this is how to apply the equation. Okay, let's consider another example. Let's see. So here's another example. If a spring has a stiffness of 950 Newton per meter, what work will be done in extending the spring by 60 millimeters? So let me get rid of this solution so that I can have space to do the working. Okay. If a spring has a stiffness of 950 Newton per meter, so this stiffness is the spring constant. So we write K equal to 950 Newton per meter. What work will be done in extending the spring by 60 millimeter? So extension here again is giving us 60 millimeter, but in this we need to convert this unit into meters. And then to do that, we will say that 1 meter equal to 1000 millimeter, right? So we divide 60 divided by 1000 millimeter. So when you say 60 divided by this guy, so you should have what do we have? You should have 0.06 meters. So this is the extension here. Now, so I can get rid of this and then write it somewhere so that we can have a space for calculation. I'm sure this is clear. Okay, I can still leave it since we have space here. So we're going to put our calculation here. So we use this work done, this equation for work done again. So work done is giving us 1/2 multiplied by Ke square. And then we substitute now. So we have 1/2 multiplied by the spring constant, which is giving us 950 Newton per meter, and then multiplied by the extension here, the square of the extension here. So and then we have found it to be this. So we are using this 0.06 square. Don't forget. So we should have 1/2 okay, let me save space because of space. Okay, so when you multiply this by this, you find the square of this. So 950 times the square of this, so we should have 3.42, then divided by 2. Yeah. So when we divide, what do we have? 3.42 divided by 2, we should have 1.71. So this is the work done. And then let's not forget to write the units. The unit is joules. So we write the units 1.71. So this is how to calculate this problem. Okay. Let's consider another example. So here is another example for us to learn. A spring of force constant 1500 Newton per meter is acted upon by a constant force of 75 Newtons calculate the potential energy stored in the spring. Okay, so as usual, we write out our parameters for easy calculation. So let's look at the parameters that we have. So we have our uh, spring constant, which is giving us 1,500 Newton per meter. So we write it out. This guy. What again do we have? We have a force of 75 newtons. Force 75 newtons. Yeah. Calculate the potential energy stored in the spring. So in this question, we will need the extension here, which is not given. So first thing first, we need to find this guy. Yes, we find this guy, and then we can now calculate the potential energy. So from Hooke's law again, from Hooke's law, we have for F is proportional to this, or directly proportional. It's given as F equal to KE. I think I explained this at the beginning of this video, so you shouldn't have problem. So now from this simple equation, we can find our extension. So we are going to have force, which is 75. So let's substitute 75 equal to constant K, which is 15 or 1500 if you want to see. So 1500 he. Therefore, our he will be, so E will now be equal to 75 divided by 1500. So when you punch your calculator, you should have something like this, 0.05 meters. 0.05 meter. So this is the extension here. Now we have gotten our extension here. We can now calculate the potential energy using this formula. So potential energy, which is given us, we can also use this formula. Yes, we can use this formula. Yeah, because force is given in this question. And if you like, you can use the other one where you have K is square, which means you are going to make use of your K constant instead of force here. But let's just use this. So you are still going to have the same answer if you use the other one. So our force is given as 75. So we say times 75, right? 75, then, so let me write it then, times our extension, he, which is 0.05. Okay. So 1 times 75 times 0.05. So let's see, we should have 3.75 divided by 2. So again, we should have 3.75 divided by 2. We should have 1.875 joules. So approximately, our potential energy approximately is going to be 1.9 joules. So if you want to approximate, so Approximately, we have 1.9 joules. This is our potential energy. Okay, so this is going to be the last example that we considered in this video. I'm sure you have learned a lot in this video. Yeah, you have learned a lot in this video, and then by now you should be able to calculate the energy in simple harmonic motion. So please, if you have any question, just write in the chat box or the comment box. I'm going to answer your questions there. Please do like this video, share it, and follow me for more updates. Thank you for taking your time to watch my video. Goodbye.